Greetings everyone and welcome to the walkthrough video for homework assignment 4, where we are going to be using Armstrong's axioms to identify candidate keys and normalize a couple of relations up to third normal form. In this assignment, you're going to be drawing dependency diagrams for each relation, identifying candidate keys using either the synthesis or decomposition method, and across the three problems, I am going to ask that you use each of these methods at least once. So as I work through these, I will solve all three using both synthesis and decomposition, so you get all that exposure, but you need to just pick one or the other, but do use synthesis for at least one and decomposition for at least one. We'll then be determining if the relations are in second normal form, and if not, we'll transform them to second normal form. Then we'll ask, well, is this relation now in third normal form? And if not, we'll transform the relations into third normal form by getting rid of transitive dependencies. So let's go ahead and get started. All right, so for problem number 1, we have a relation with these 6 attributes, A, B, C, D, E, and G, and 3 functional dependencies. A functionally determines B, E functionally determines D, and EG functionally determine AC. So the first step here is to draw the dependency diagram for the relation, and I'm going to do that using PowerPoint. So this is going to be kind of similar to some of the PowerPoint drawings we have done before. I'm just going to start with this blank presentation by deleting the stuff that's there, then go to my Insert tab, select Shapes, and I'm just going to draw a couple of boxes about that big. And I'm going to change my shape outline to black and my shape fill to white. Then I'm going to double click in here to put the name of my attribute. I'm going to say A, which we don't see to begin with because that text is in white by default. So I'm going to go change this to black. And now we have a box representing one of our attributes. So I'm just going to copy and paste this and let it snap into place here. Copy all 3 of these just to make things a little bit faster. And update these boxes to represent the attributes we're interested in. So A, B, C, D, E, and G. And now we're going to draw some directed arcs, or just series of lines with arrows on the end, to represent our functional dependencies here. Now, one neat thing in PowerPoint, if you hold the Shift key while you draw a line, it will snap to the common angles of 0, 45, and 90. So I'm going to draw just a straight line there. I'm going to make the outline of that black. And I'm going to just copy and paste this to do something that looks kind of like this. And now a couple of changes we need to make. One, we need to have an arrow pointing down at B. So I'm going to highlight that segment, and in the shape outline drop down, go down the arrows, and I'm going to put an arrowhead on the end of this. And that was the wrong direction, so depending on which way you drew your line, it really could be either of these. It's a little hard to tell, but I'm going to switch to this one. And there we go. Now our arrow is pointing down at A, or at B. So A functionally determines B. And just to make this a little prettier, I'm going to make these lines a bit bolder. Let's go to maybe a 4-point line, something like that. All right, so that's our first functional dependency. A functionally determines B. And then I'm just going to copy this. We need E determines D. So I'm going to do like that and then just kind of drag this over. All right, and then our third functional dependency, EG, functionally determines AC. So I'll once again just kind of paste this. And I'm just copying and pasting these segments so that I don't have to redraw them so often, and kind of dragging them into place. So for a composite determinant, I'm going to make it look something kind of like this. We say e.g. functionally determines A, C, all right, so now we have, functional dependency 1, A determines B, functional dependency 2, E determines D, and functional dependency 3, E, G together determine A and C. So now we have our dependency diagram. So I'm going to take a screenshot of this and paste that into my document. And wow, that's way too big. So I'm going to shrink this down a bit. A size like that is kind of appropriate. And so that is 1A. Now moving on to 1B, we want to identify the candidate keys for this relation using either the synthesis or decomposition methods. So I'm going to start with synthesis, and then we'll do decomposition next. So for this synthesis method, I'm going to find the closure of all of the interesting determinants here. So the closure of A is going to be, of course, through reflexivity, A, and based on functional dependency 1, B. And if we know A, I don't think there's anything else we can determine. So the closure of A is just going to be AB. Looking at our next determinant, E, we could say the closure of E is going to be, of course, through reflexivity, E, and through functional dependency 2, E determines D. So D will be in the closure. And then I don't see anything else that E or D can functionally determine. So I believe that's going to be it for the closure of E. And then finally, let's look at the closure of EG, which is going to, of course, have E and G. And then based on functional dependency 3, also A and C. And since EG determines A and A determines B, then through transitivity, we could say EG also determines B. And since E determines D, and we know the value for E, then we can also say EG functionally determines D. I believe that is everything we can get. EG functionally determines EG, A, C, B, and D. And items in a set are not ordered, so it doesn't matter if you write this as A, B, C, D, E, G, or E, G, A, C, B, D. That means exactly the same thing. But it looks like at this point, we can functionally determine every attribute in the relation based on EG. So that means we're going to have a candidate key of EG. Excellent. So that is the synthesis process. If we wanted to do the same thing with decomposition, we know we have at least one superkey in the relation, which is going to be all the attributes in the relation. So A, B, C, D, E, G, we know is a superkey. So now we're going to attempt to systematically remove one attribute at a time from this superkey and ask if the superkey without that attribute can functionally determine the attribute that we just removed. So we're going to say K prime is A, B, C, D, E, and we're going to ask, does K prime functionally determine G? And in this case, it doesn't look like anything functionally determines G. So we're going to say no, and that means we have to include this attribute G in order for this set of attributes to be a superkey. Okay? So we're going to try again, and we're going to set our value of K prime to be A, B, C, D, G. Okay, because we're adding this G back in because it is required for this to be a superkey, but we're taking out another attribute E. And we're asking, does K prime functionally determine the attribute we just removed, E? Well, looking back at our functional dependencies, it doesn't appear that anything functionally determines E. And we can see that in our dependency diagram too. There's no arrows pointing at E or pointing at G. So the answer here is going to be no, meaning we have to put E back in order for this to remain a superkey. So we'll try once more. We're going to set our value of K prime to be A, B, C. We have to put our E back in, and we already put G back in, but this time we're taking out D. And we're going to ask, does A, B, C, E, G functionally determine D? Well, it looks like as long as we have a value of E, we can use E to functionally determine D. And we have E, so that means we do not need D. So this set A, B, C, E, G is a superkey even without this attribute D. So we can get rid of that. We don't need that to remain a superkey. So let's try again. We're going to set K prime to be A, B, E, G. And we're going to ask, does A, B, E, G functionally determine C, this attribute we just removed? So it looks like if we know EG, we can functionally determine C. So since we know EG, then we can functionally determine C, so we do not need C in order for this to be a superkey. So we can remove C. Now let's try one more time. We'll set our value of K prime to be A, E, G. And then we're going to ask, can K prime functionally determine the attribute we just removed, which in this case is B? And we see in our functional dependencies, as long as we know the value of A, we can functionally determine B. So the answer there is yes. Since A determines B, AEG can functionally determine B. So we don't need this attribute in order for this to remain a superkey. And I believe this is our last one we're going to have to try. We're going to set K prime equal to EG. And then we're going to ask the question, does K prime functionally determine A? And here we see EG functionally determines A. So as long as we know EG, we can determine A, and that is what we have remaining in this superkey. So we do not need A. So now we know this is a superkey. We have tried to remove every single attribute, and so now we know that we have a superkey that is irreducible, and therefore that is going to be a candidate key. So EG is a candidate key for this relation. Now, regardless of the method we used, synthesis or decomposition, we want to see if there are any additional candidate keys that we can derive. And the way we do that is to look at all of the attributes that make up whatever candidate key we have found, and look back at our functional dependencies and see if any of those attributes are dependents in any of the functional dependencies. So in this case, I don't see E or G as a dependent in any of our functional dependencies. So at this point, I think we have just this one and only candidate key of EG. So that is going to be our answer there. Now, question 1C asks, is the relation in second normal form? Now, recall that a violation of second normal form is a partial dependency, and that's when you have a non-key attribute that is being functionally determined by a part of a candidate key. So in this case, we have a candidate key of EG. So we have two key attributes, E and G, and A, B, C, and D are all non-key attributes. So this A functionally determines B, that is not a violation of second normal form, but functional dependency 2 here, E functionally determines D, well, that is a part of this candidate key functionally determining a non-key attribute. So we have a key attribute functionally determining a non-key attribute. That is a partial dependency, and that is a violation of second normal form. So is this relation in second normal form? No. Why or why not? Because FD2 E determines D is a partial dependency. So we are not in second normal form. And now question 1E asks us to write the relations in second normal form, identify the functional dependencies and candidate key or candidate keys for each relation. So the way we're going to get this from first normal form into second normal form is by taking this problematic undesirable functional dependency of E determines D and moving that out into a new relation, leaving the determinant behind in the original relation. And that determinant in the original relation is going to be a foreign key that refers to this attribute in the new relation. Okay, so I'm going to create a new relation, just call it R2, and it's going to have the attributes D and E in it with a functional dependency of E functionally determines D, and it's going to have a candidate key of E, because E can functionally determine everything in this relation. E determines itself, and E functionally determines D based on functional dependency 1. Okay, so we've created a new relation, or essentially a new table in our database containing these two attributes. And then remaining in our original relation, R1, is A, B, C. D has been moved out, but we leave the determinant E behind, and G, A, B, C, E, G, with these functional dependencies of A determines B, and EG functionally determine A and C. And in this relation, we still have our candidate key of EG, right? Because the closure of EG contains every attribute in the relation, EG, AC, and B. And recall, we left the determinant behind in this relation, E, because now this is a foreign key that refers to this attribute E in the new relation. So that's how we can join these relations back together. Now, question 1F, are the relations provided in question 1E in third normal form? So recall, a third normal form violation is when we have what we call a transitive dependency, which is when a non-key attribute functionally determines another non-key attribute. Well, in this case, both A and B are non-key attributes, okay? So this is a transitive dependency and a violation of third normal form. So no, we are currently not in third normal form. And that is because functional dependency 1, A determines B, is a transitive dependency. And now we're asked to write the relations in third normal form here, along with the functional dependencies and candidate keys for each relation. So I'm going to create another relation and call it R3, and it's going to have the attributes from this problematic functional dependency, A and B with a functional dependency of A functionally determines B. So now A is a candidate key in this new relation we've just created because A functionally determines both A and B. So our candidate key here is A. And then relation 2 up here was not impacted by any of this. And then our original relation 1, since we are doing this, we need to leave behind the determinant A, but we're going to get rid of the dependent B, and we're getting rid of this functional dependency here. So we have normalized this by taking what were two problematic functional dependencies. E determines D, which was a partial dependency, and A determines B, which was a transitive dependency, moving these attributes and their functional dependencies out to two new relations, leaving behind the determinants A and E so that we can recreate this through joins. Okay, so now we have three relations. Relation 3 with the attributes A, B, and the functional dependency A determines B, and a candidate key of A. Relation 2 with the attributes D and E, the functional dependency E determines D, and a candidate key of E. And then our original relation 1 is now just left with the attributes A, C, E, G, with the functional dependency of EG determines AC, and a candidate key of EG. Okay, so now EG functionally determines everything in this relation. E is going to be a foreign key now that refers to this candidate key E in relation 2, and A is a foreign key that refers to this relation or this attribute A in relation 3, which is a candidate key in this relation. So this is the answer to number 1. Moving on to number 2, we have a new relation with these attributes A, B, C, D, E, F, G, and these functional dependencies here. So let's go ahead and start by drawing our dependency diagram. And I'm just going to use my diagram from last time as kind of a starting point. I'm just going to move some of this stuff out of the way. So A, B, C, D, E. Now we have F and G, so we'll do that. Functional dependency 1 is that E determines C and G. So E determines C and G. So that will look something like that. F and G together functionally determine A, B, and E. So F and G together functionally determine A, B, and E, and then B and C together functionally determine D. So B and C together functionally determine D. See if I can make this just a little bit neater. All right, I believe that will suffice. So I'll go ahead and get my screenshot here. And note there is a little warning here that we're going to have to infer a couple of additional functional dependencies during our transformation from second normal form to third normal form. So we'll talk more about that in just a moment. But before that, let's go ahead and identify all of our candidate keys using either synthesis or decomposition. So I will start with synthesis. So let's find the closure of E. So the closure of E is going to be E, C, G. And if we know E, C, and G, is there anything else we can figure out? Well, I don't think so, right? Because we don't know F, so we can't do anything with this, and we don't know B, so we can't do anything with this. So I think the closure of E is just ECG. Let's look at the closure of FG. So F and G together, of course, can determine F and G, and then also A, B, and E. So A, B, E. And if we can determine F, G, A, B, E, we got E, so we can also get C and G. So we already know G, but C is a good addition. And so this is getting very close. A, B, C, E, F, G. So we just need D. And since we can functionally determine C, we now have both B and C, which together functionally determine D. So that's also going to be in the closure A, B, C, D, E, F, G. Oh, that looks like everything. So it looks like FG is going to be a candidate key. At this point, it's not super important then to find the closure of BC, but we can go ahead and do that for fun. So of course, B and C will be in the closure because of reflexivity, and BC functionally determines D. So that will also be in the closure. And then if we know B, C, and D, I believe that's where we stop. So we have this one set of attributes, FG, which is going to be a candidate key. So now we want to identify if there are any other candidate keys in the relation. And we do that by asking, are any of the attributes that make up this candidate key are dependents in any of our functional dependencies? And in this case, the answer is yes. E functionally determines G, right? So anywhere we have a G, if we know the value of E, we could figure out that value of G. So we can replace any G with an E. So we also have a candidate key of FE. Okay, now are any of these attributes dependents in any of these functional dependencies? And yes, E also is, right? So anywhere we see an E, we could put FG. Okay, so that's going to be FG, and we don't need this repeated attribute here, so this just turns into FG, which is the same candidate key we had already identified. So once we get into a situation where we're finding candidate keys we have already found, that's a good signal to us that we have identified all of the possible candidate keys in the relation. So we actually don't need to repeat FG, we can just stop here and know that FG and FE are our two candidate keys. So that's the synthesis process. Let's go through the same thing using decomposition. So we're going to start with this known superkey of A, B, C, D, E, F, and G. And then we're going to set a value for K prime to be A, B, C, D, E, F. And we're going to ask the question, does K prime functionally determine G, right? Because this is that entire superkey with just one attribute removed. Okay, so if we know the values for A, B, C, D, E, F, can we determine the value of G? Well, it appears E functionally determines G, so as long as we know E, we can determine G. So the answer is yes, meaning we do not need G in order for this to remain a candidate key. Okay, so we'll take that out and we'll set K prime to be A, B, C, D, E, and ask the question, does K prime functionally determine the attribute we just removed, F? If we know A, B, C, D, E, can we determine F? And that does not appear to be the case. None of our functional dependencies let us know the value of F. And we can see in our dependency diagram, there's nothing pointing to F, right? Nothing functionally determines F except for F in this case. So the answer here is no, meaning this is not a superkey. We need to add F back into this set of attributes to make that be a superkey. So now we're going to set a new value for K prime, which is going to be A, B, C, D, F, and we're removing E, right? Now we ask the question, does K prime functionally determine the attribute we just removed, E? Does A, B, C, D, F functionally determine E? Okay, here's E, but we need both F and G to functionally determine E in this case. We have F, but we don't have G, right? So we cannot functionally determine E based on A, B, C, D, F. So the answer here is no. We need to put E back into the mix, and we'll try removing something else. So let's ask, does A, B, C, we got to put E back in, E, F, does K prime now functionally determine the attribute we just removed, which is D? Okay, does A, B, C, E, F functionally determine D? BC determines D, and we have both B and C, so the answer there is yes, meaning we can get rid of D, no problem. So now let's set a value for K prime to be A, B, we're going to try removing C, and we know we need E and F. So now does K prime functionally determine the attribute that we're removing, C? Does A, B, E, F functionally determine C? E functionally determines C. And we know E, so the answer there is yes. We can safely remove C from the set of attributes and it will remain a superkey. Okay, just a few more. If we make K prime A, E, F, and then we're going to ask the question, does K prime functionally determine B? Does A, E, F determine B? Okay, so to determine B, we need F and G. But since we know E functionally determines G, so through pseudo-transitivity, we can also say F and E together can determine A, B, E, right? So in this case, the answer is yes, right? And this is because of functional dependency 1 and functional dependency 2 together. So we don't need B in order for this to remain a superkey. And then we'll try one more here, making K prime E, F. And then we're going to ask the question, does K prime functionally determine A? If we know the values of E and F, can we determine A? And kind of a similar situation here, E determines G. So that means that as long as we have the value for E, we can determine G. So FE would functionally determine A, B, and E. So the answer there is yes, again, because of functional dependency 1 combined with functional dependency 2, meaning that we have a candidate key of FE, which is, of course, one of the candidate keys that we originally found, and it was the second candidate key. It doesn't really matter what order we find these in, but through decomposition, we identified this candidate key of FE. Are either of these attributes dependents in any of the functional dependencies? And in this case, yes, E is functionally determined by FG. So anywhere we see an E, we could put an FG, which would look something like this. We don't need this duplicate F, so this is FG, right? So this is the same candidate key that we found through synthesis. These are both the same candidate keys that we previously found. So that's our answer here, is that we have two candidate keys, FE and FG. Now, is the relation in second normal form? And again, a violation of second normal form is when we have a partial dependency or any non-key attribute that is being determined by just a part of one of these candidate keys. Okay, so if we have just F, E, or G as a determinant, that is going to be a problem. This functional dependency 1, E determines C and G. So E determines G is actually totally okay because G is a key attribute, okay? A key attribute functionally determining another key attribute is not a second normal form violation. C, on the other hand, is a non-key attribute. Okay, so E functionally determines C is going to be a problem we need to resolve. And this might be a little easier to see if we just go ahead and decompose functional dependency 1 into two functional dependencies. E determines G. So this E determines G is perfectly okay from a second normal form perspective. This E determines C, however, is a problem, okay? So we're going to say, no, we are not in second normal form. Why or why not? I'm going to say functional dependency 1A, E functionally determines C is a partial dependency. And while it's not required here, if we wanted to be even a little bit more complete in our answer, we might go on to say E functionally determines G, however, is not a 2NF violation since G is a key attribute. Okay, now 2E, write the relations in second normal form here with the functional dependencies and candidate keys for each relation. So we're creating this new relation, relation 2, with these attributes from the problematic functional dependency, C and E, and the functional dependency of E functionally determines C. And our candidate key for this relation is going to be E. And then for relation 1, we're going to have the attributes A, B, C. We've moved out to this other relation, D, E, F, and G. Now, when we created this relation, note again that we left the determinant E behind, and so E in this original relation 1 is now a foreign key that refers to this candidate key in the new relation. And I am just going to copy my functional dependencies down here. And this is the problematic functional dependency, which we just moved up here. So we're going to get rid of this. But before we do, let me point out a problem that removing this attribute C is going to create, and that is that C is part of the determinant in this functional dependency 3. So we can't just get rid of C because BC functionally determines D. However, since E functionally determines C, through the magic of pseudo-transitivity, we can derive another functional dependency here that can take the place of functional dependency 3, which is that BE also functionally determines D, right? So at that point, we can get rid of this functional dependency that was causing the problems, and we are left with this situation. And we still have the same two candidate keys that we did before of E, F, and FG, or FE and FG. Again, the order doesn't matter for these. And while it is not required in the assignment, I do have a drawing of the dependency diagram here that I will just share with you that goes along with this. All right, now the next question, are both of these relations in third normal form? Okay, so relation 2 with these two attributes C and E and this one functional dependency of E determines C, this is in third normal form. We're totally in good shape with this. However, for relation 1, with these two candidate keys of FE and FG, I believe we are good with regard to partial dependencies because we said both E and G here are key attributes. FG determines ABE, that is the entirety of one of our candidate keys, functionally determining some other attributes. But then functional dependency 3, BE determines D. Well, B and E together, even though E is a key attribute, this combination of BE, that will be a composite non-key attribute. So the answer here is going to be no. And the why or why not, it's because BE functionally determines D is a transitive dependency. So in order to resolve that, we're going to create a new relation, relation 3, which is B, D, E, with just one functional dependency of BE determines D. And a candidate key of BE, because of course BE functionally determines B and E through reflexivity and determines D through functional dependency 1. So BE functionally determines every attribute in the relation. We said relation 2 was already good and in third normal form. And then relation 1, with these functional dependencies, we have to leave BE behind to be a candidate key in this relation, but we got rid of the attribute D and this problematic functional dependency here. So we wind up with these three relations, and again, it's not asked for, but this is what the dependency diagrams would look like here. So one thing to point out is that as we're working through these problems, each one of the relations has its own normal form, right? So in this case here, this relation is normalized up to third normal form, while this other relation is still in second normal form because we have this transitive dependency of BE functionally determines D. So at this point, once we've resolved that, all three of these relations are in third normal form. Now, one other thing I will point out is even though we are in third normal form here, we do have a Boyce-Codd normal form violation. right? And remember, Boyce-Codd normal form violations are possible when we have at least two candidate keys, which is the case here, which are both composite, which is also the case here, and in which we have an overlapping attribute, which is the case here, right? We see F in both of these candidate keys. And we know this is a problem because we're going to have a determinant that is not a superkey in the relation, and that's what we see here in functional dependency 1b. E is not a determinant in the relation, so this has the potential to still introduce data redundancy into our design. However, this is not a second normal form violation because E and G are both key attributes. So while this is where I'm going to have you stop in the assignment, if you wanted to take this just one step further and resolve that Boyce-Codd normal form violation, you would wind up with something that looks like this, where you have these four relations. So just something to kind of think about there. All right, and last but not least, number 3. And number 3 looks a little bit different because instead of these attribute names like A, B, C, D, E, F, G, here we're using some attribute names that might actually be found in a database. And in this case, this looks like a relation that is perhaps tracking tour dates for a band that is going on tour to different concert venues in different cities and states in support of some album that they have recently released. So this concert is going to be associated with a particular album that they are touring to promote. So we have these attributes of artist, album, year, length, genre, date, concert venue, city, state, and capacity, and these functional dependencies here. So I'm going to suggest just that in order to save yourself a little bit of writing and to not get so confused about the details of what these data might mean, you might want to replace each one of these descriptive attribute names. So I'm going to go ahead and show you what I did here to make that translation, but I'm not necessarily going to take the time to go click by click through it on the video. But essentially, I just said this attribute artist, we're going to call A, album we'll call B, year we'll call C, and so forth down the line. And then rewrote the functional dependencies using those letters instead of the full names. And then for the dependency diagram, I just kind of did the same thing so I can kind of look back and forth and think about these attributes either by their full name or by the letters that I have given them. Great, now on to identifying our candidate keys. Again, let's just start with the synthesis method. So the closure of A is going to be A, E, and I believe that is it. The closure of A, B is going to be A, B, C, D. And I believe that's it for that. The closure of FG is going to be FG, A, and then everything that's in the closure of A, which includes E. So F, G, E, oh, H, I, and J. H, I, J. And I believe that is it for FG. The closure of AF is going to be AFG. And let's see, since we know A, we also know E, so we can add that into our closure. And I believe that is it there. And finally, let's find the closure of G, which actually we know we're not going to have any use for because we have the closure of FG, which is guaranteed to be bigger than the closure of G. But just for fun, G is going to contain G, H, I, and J. And I think we stop there. So it looks like our most productive closure is of FG, and we get the attributes A. We don't have B, C, or D. We do have E, F, G, H, I, J. So we need to get B, C, and D, which can all be functionally determined by AB. Well, and we already know A, so really we just need to add B to F and G. So let's see how that works. So if we had B, F, and G, the closure of that would be, of course, B, F, G, A, E, H, I, J, and since we know A and B, that functionally determines A, B, C, D. So we've already got A, B, add C and D here. So the closure of BFG is A, B, C, D, E, F, G, H, I, and J. So that is all of our attributes. So that is a good candidate key. E, F, and G. And so now we want to see, are there any other candidate keys? Can we functionally determine any of these key attributes, B, F, or G? So it appears AF functionally determines G. So anywhere we see a G, we could put AF. So B, F, A, F. We don't need the other F because we've already got that here. So BFA would be another candidate key because FA functionally determines G. So BFG and BFA. And FG functionally determines A. So anywhere we see an A, we could put FG, right? So we could say BFFG, and we don't need this repeated F. So that's BFG, which is just the same candidate key that we identified originally. So now we're in that loop. We know that there are not any additional candidate keys. So I think we just have these two candidate keys, BFG and BFA. Or another way to say that would be album, date, and concert venue, or album, date, and artist. Let's go ahead and walk through this with the decomposition method as well. So we start, we know we have a super key of A, B, C, D, E, F, G, H, I, J. We're going to set K prime equal to A, B, C, D, E, F, G, H, I without the J. And we're going to ask, does K prime functionally determine the attribute we just removed, J? So looking up to our functional dependencies, it looks like as long as we know the value of G, we can figure out J. So we'll say yes, because G functionally determines J. So we can remove J and be perfectly okay as long as we still have G. So we'll try again. We'll set K prime to be A, B, C, D, E, F, G, H. And we're going to ask, does K prime functionally determine the next attribute we're removing, which is I? And I think we previously just saw that G determines H, I, and J. So the answer is yes, because G functionally determines I. So we'll try again. We'll set K prime equal to A, B, C, D, E, F, G. And we asked, does K prime functionally determine H? And again, the answer to that was yes, because G functionally determined H, I, and J. So we'll try again. We'll set K prime to be A, B, C, D, E, F. And we ask the question, does K prime functionally determine G? Okay, I'm not sure. Let's go back and look. A and F functionally determine G. So do we have A and F? Yes, we have A and F. Yes, because AF functionally determines G. So we can actually get rid of G because AF determines G and G determines HI, So AF would also determine HI and J. So we don't really need that G that seemed pretty important just a moment ago. So we'll try again. Let's set K prime to A, B, C, D, E. And we say now, does K prime functionally determine F? So F is not functionally determined by anything, right? And again, in our dependency diagram, we don't see any arrows pointing to F. So F is the only attribute that can functionally determine F. So that's got to be pretty important. The answer there is no. So we need to put F back into this set of attributes in order for it to be a superkey. A, B, C, D, E is not a superkey. So let's try once again. We'll set K prime to be A, B, C, D. We're going to try to remove E, but we have to put F back in the mix. So we say, does K prime functionally determine the attribute we just removed, which is E? A determines E, and we have A, so the answer is yes, because A determines E. Excellent. Try again. Does K prime, or if we set K prime to A, B, C, we're going to try removing D this time. So we're just A, B, C, F. Does K prime functionally determine D? A, B, C, F. A and B determine D. So as long as we know AB, we can functionally determine D. So AB functionally determines D. So we can get rid of D. Almost there, everybody. Now let's try removing C. So we're going to set K prime to be A, B, F. And ask, does K prime functionally determine C? Does ABF determine C? There we go again. AB functionally determines C. We have AB, so yes, because AB determines C. Okay, so now we'll set K prime to be AF. And ask the question, does K prime functionally determine the attribute we just removed, B? Does AF determine B? I don't see anything that determines B, so I think B must be important to keep in there. So we'll try one more, setting K prime to be BF. And then ask the question, does K prime functionally determine A? We know BF, can we determine A? Well, if we know FG, we can determine A. If we know AF, we can determine G. but I don't think there is any way just B and F together can determine A. So I think we have to put A back in there, and we're going to wind up with a candidate key of A, B, F, which, notice, is one of the candidate keys that we identified earlier. The attributes are in a different order, but that's okay. These sets of attributes are not ordered, so ABF is the same as BFA. And then, are there any other candidate keys here? Are A, B, or F the dependents in any of these functional dependencies? Well, yeah, A is. So we can replace A with FG. So we could say FG, B, F. And we already have F, so we don't need that again. So FGB, which is the same as BFG. Okay, so as expected, we identified the same two candidate keys through decomposition that we had already identified through synthesis. So is this relation in second normal form, right? So we want to make sure we don't have any partial dependencies or any non-key attributes that are being determined by part of one of our candidate keys. And just to make this a little easier, I'm going to put our candidate keys that we've identified right here under our functional dependencies. And yeah, I think we may have quite a few issues here. So here in functional dependency 1, E is a non-key attribute that is being determined by part of a candidate key, right? So that is a partial dependency. AB, okay, that's part of this candidate key, and it's functionally determining CD. These are two non-key attributes, so this is also a partial dependency. FG determines A. This looks like it might be a partial dependency. However, A is a key attribute. Okay, so this actually is not a second normal form violation. And similar story with functional dependency 4. Even though AF is part of one of our candidate keys, G is a key attribute. Okay, so this is part of a candidate key functionally determining a key attribute. That's not a great thing, but that is not a violation of second normal form. A violation of second normal form, the dependent must be a non-key attribute. Now for functional dependency 5, G is part of a candidate key, and it is functionally determining three non-key attributes, H, I, and J. Okay, so we actually have three partial dependencies here. So no, it is not. Why or why not? Because these three functional dependencies are partial dependencies. All right, so let's resolve these three second normal form violations. So we're going to do that by one at a time, just moving these problematic functional dependencies and all of their attributes out to a new relation. So we'll kind of start at the bottom here and just say relation. We're going to create three. So we'll have a relation 4, a relation 3, relation 2, and relation 1. So relation 4, we'll put G, H, I, and J in with this functional dependency of G functionally determines H, I, J, and that is going to have a single candidate key of G. Relation 3 is going to have the attributes A, B, C, and D in it, with a single functional dependency of A, B functionally determines C, D, and a candidate key of AB. Relation 2, we'll just have these two attributes, A and E, with a functional dependency of A functionally determines E, and a candidate key of A. And then relation 1, we're going to have all the attributes that were originally in relation 1, except for everything that we've moved out to other relations. But everything we've moved out to other relations, we need to leave the determinant behind as a foreign key. Okay, so we're going to have A and B. We've moved C, D, and E out to these other relations, but we've left behind F. We had to leave behind G when we moved that functional dependency. So we're going to have A, B, F, and G. And it's going to have these other two functional dependencies we started with. FG determines A and AF determines G. And then it's going to have the candidate keys that we previously identified of BFG and BFA. And while I did not ask you to provide this, if you're interested, this is what the dependency diagram for these three relations would look like. So a couple of things I will point out here. Notice that in relation 1, nothing functionally determines B or F, and that's why we see B and F in both of our candidate keys. But if we know A, B, and F, we can determine G, and if we know B, F, and G, we can determine A. Okay, so we have no partial dependencies, no transitive dependencies. However, we do have a BCNF violation, a Boyce-Codd normal form violation, because we have these multiple candidate keys that have that are composite and that have some overlapping attributes, B and F. And we see this played out in that neither one of our functional dependencies is the determinant A superkey. Now, all of these other relations are in first, second, third, and Boyce-Codd normal form. And we could bring everything back together by just joining based on the determinants that we left behind, right? So A is a foreign key that refers to A in this relation 2. AB together is a foreign key that refers to AB, the candidate key in relation 3. And G is a foreign key that refers to the candidate key G in relation 4. So at this point, we've gotten rid of our partial dependencies, and we also don't have any transitive dependencies. So once we fix those second normal form violations, we are already in third normal form too, because we have no transitive dependencies. And you could just copy and paste your answer from here, or just write, same as question 3E, something like that. All right, that's it for assignment 4. So with this knowledge, go forth and do great things.